As you can see behind me, I was on the international organizing committee of this conference. And when it was announced, I don't remember what, I had some comment to make, and I sent a message. This is a great conference to Danielle. I will come to it and I will enjoy not having to give a talk because I had already seen the program. And then the program changed, and here I am. And as you know, I can not say no to anything. And so then worse than that, I mean, this was my task. And so what's the answer to this? And, you know, other things happened to me in the last few months, so I had no time to think about it until last week or so. And that was my first answer. And then I thought about it some more, and I mean, actually came up with something. By the way, you are looking at a picture of the South Pole yesterday morning, but you know, it's morning for 6 months now. So that's the ice cube experiment, but of course it's everywhere a mile below here, and that's the South Pole telescope. So what did I come up with? And so I was thinking about the history of particle physics, and it's here on this slide. There was a time particle physics started, of course, with cosmic rays, and there was a prehistory, like from cosmic rays to 1977, when it was totally driven by experiment, with notable exceptions. But, you know, it started with discovering the muon and the famous question of Rabi, who ordered that, which we still haven't answered. And then, you know, one surprise came after another, including the neutrino, kaon, CP violation. And so this field was full of surprises. And then, of course, it stopped. And the standard model came. The depressing thought is that the first textbook appeared in the early 80s already. And so then the most successful theory ever constructed only led to precision tests where we saw what we looked for with better and better precision and no more. There is always the discussion at this meeting about the role of theorists. I mean, this is the place where theorists play a role and can shine, and even can occasionally predict something like the Jim mechanism. This is a tough time for theorists. And of course, there must be a beyond the standard model, and maybe the lepton universality seen in B decay by the LHC B experiment or G-2, there is hope. So my remark was, the thing I told about is, this period never happened in neutrino physics. And in neutrino physics, you design an experiment, you go and look to measure something, you find it with better precision. You know, all the so-called discoveries in neutrino physics were things we would go and look for and had to corner the neutrino to give the secret away, including, you see here the list, I'm sure people are going to find exceptions to it, but even at the end, we build ice cube for cosmic neutrinos, and the biggest surprise is that that's what we are doing. And so the supernova was not a serendipitous discovery. The IMB proposal clearly stated that this was one of the goals of the experiment. So maybe we have some crazy exceptions too, sterile neutrinos, and I will explain to you what this is later, unless I forget. But of course, whether these are surprises, we don't know yet. And so, to use the words of Mark Bowen, a science writer, the neutrino is a coy mistress. The neutrino doesn't give away secrets easily. So this is really a different story. And so, you know, what does this mean about the future? It means about the future is that we have to keep building dedicated and exploratory experiments. And I think our main goal now is, and thanks for the introduction in the previous talk, is to find neutrino physics beyond the standard model. I think whatever the LHC people think, I hope they find physics beyond the standard model, but I think we have a shot at this that's as good as them. And so if we want to do it, it will not happen by accident. We have to do the same as in particle physics, do precision experiments, and then do dedicated experiments to go and find it. So in this sense, the future is bright, because a lot of instrumentation, especially the few historians in this room, I don't want them to think, I think if I have one role is to tell them that there is a future to this field, which most likely will be more exciting than the past. In the precision range, the development of very intense accelerator beams will have helped the field. There is a short baseline program, there is the Dune program at Fermilab, there is Hyper-K, there is ORCA, I will tell you what that is if you don't know. There are neutron factories, the neutron factory in Lund that creates new opportunities to do neutrino physics. And unfortunately, this is one of my favorites. It has never been, I don't think it has been mentioned at this conference. In 2006 or 7, I was actually chairing a committee where ECFA asked us to investigate the spectrum for future oscillation experiments between neutrino factory and long baseline. And as soon as the ink was dry on that report, Theta 1-3 was discovered. And neutrino factories disappeared from the face of the Earth, and everybody went to do a cheap long baseline experiment, or now a not so cheap long baseline experiment. But I think we should keep it in mind. There is new exploration to be done. I think double beta decay is an old example of a great exploration experiment. We should not be shy of building supernova detectors. There are very few dedicated, as far as I know, dedicated supernova detectors being built, big ones at least. The short baseline reactor beams are a new entry with the possibility of new discovery, but also neutrino telescopes can play in this game, as I will tell you later. And of course, the results of all this will be in the next conference, which will be organized by Danielle and Michel. And you saw the prediction in the talk this morning based on string theory. I expect you to be there. So let me first start with the bread and butter, the oscillation experiments. This is a beautiful plot made by Carlos Argüelles. It's the baseline versus the energy of the neutrino. And so it gives the landscape. Here is the solar territory, the atmospheric, and here may be the 1eV LSND territory. So let me first say something about the LSND. This line represents the line where delta m square is 1eV square. And so certainly, whether motivated or not, whether you can combine these things or not, it's something to look for. And I just, as I said, most of this is going to be based on IceCube. We had a beautiful opportunity, because not only are we on this line, but it happens that neutrino oscillations propagating through the Earth make a resonance at the energy of 3 TeV, where we have most of our neutrinos. And this resonance appears because the electron neutrino, when it's sterile, loses its matter interactions. And that makes this resonance, all your muons disappear and reappear as taus. Well, here is one example, one set of data. Here is the neutrino flux as a function of energy. This is the zenith angle distribution. If there were any sterile neutrino, there will be a dramatic structure in this, and you don't see anything. And then what do? You set limits, which I'm not very interested in. I'm too old for limits. But this, we are now bringing out, within weeks actually, 7 years of data. You just looked at 1 year of data. And there is a short baseline program at Fermilab. And there are these very short baseline experiments where you put a detector at 5 meters or so from a reactor, a research reactor. And so there is a lot of opportunity. So hopefully something will come out of this. So let's go back, however, at more realistic cases. We had, of course, you heard at this conference that this was the work of many people, and unfortunately, we didn't get any hint from these experiments. You know, it's fantastic quantum mechanics, it's another matrix. It could have been something simple like that, and then we could have been inspired. Of course, this picture is already spoiled by discovering theta 1-3, with a big angle as well. And so it's complicated. Here it is. That's the matrix. And that's just like another matrix we don't understand, the CKM matrix. But note, however, we learned something interesting from this matrix. We actually learned something about CP violation in the quark sector. So maybe don't give up hope yet. But it's not simple message to read. So let me tell you a story about, again, back to IceCube. We have 500,000 neutrinos, and someone had the idea, well, let's just do an oscillation analysis on it. And the proposal clearly stated that this was not our business, and it was run and got 5 sigma and was published. And here it is. And the reason we could do this, actually, we had never thought about. Here is where the rest of the world does neutrino oscillations. Sorry. We do neutrino oscillations where it's easy, in this big first dip that we map out, which is really easy. And we can connect it to data where neutrinos don't oscillate. And so because it's easy, we got this result immediately. We could actually make an LE over E plot, which, as you know, is not easy in these experiments. And so that's the status now. Now, you have to understand, we are not doing this to compete with these other experiments. We are doing this analysis at 5 GeV and above, up using, in the range, actually, 5 to 55 GeV. And so our goal is to find different oscillation parameters and find new physics, because we are doing it an order of magnitude higher in energy. And so then we begin to doubt it. I mean, if we find this, will anyone believe us? And so this was, by the way, this shows the difference in energy range. So don't read this slide. So what we did is actually, and this was not planned, it developed by accident. 2 groups started analyzing the IceCube data. They basically didn't talk to each other, and one went after statistics, and the other went after golden events. Totally different. And you can study this from my slides. No critical aspect of the analysis was in common. Different cuts to select a sample, different reconstruction. The only thing that's in common is trivial assumptions in the Monte Carlo. Different systematic errors because they were so different. And so, as you know, as many of you know, IceCube is the most conservative collaboration that ever existed. And so I was not involved in this, I was doing other things, thought they are going to learn that they have overestimated their systematic errors. Well, this is the result. This is one analysis, and this is the other. So I let you decide. This is a sociological exercise, what you decide of this. And what I learn of this is that you don't even know when you're not conservative. Because systematics is not scientific, it's judgment. It's not science. And the other thing is that you really have to, you really have to be careful with systematic errors. Of course, if we really understood systematic errors, they wouldn't be systematic. So tau appearance, by the way, was discussed a lot. This is the status. It's not that bad, actually. These are the two ice cube analyses, Super K and Opera. And so it's kind of in the right place. We are just funded to do an R&D experiment where we are going to deploy strings to develop new ice cube technology, but we're going to put the strings inside the high density core of the detector so that we can do oscillations better. And again, we will emphasize trying to measure tau appearance to better than 10%, and this is happening now. But the real future of this is the Orca experiment, which is about to start deploying 5 or 6 strings, I've forgotten. And it's a much bigger experiment that's dedicated to doing oscillations in the Mediterranean. It's an off-spin, of course, of the existing Antares experiment. And you see the short string spacings on this experiment and the high density of photomultipliers. So now, why would we continue doing this? And I was a member of the P5 committee who recommended Dune and the long baseline experiment. And so I'm sick of discussing this question, and because it was discussed. And so the excuses are usually that we may learn something about leptonic CP that may be connected to baryogenesis and the whole idea of antimatter versus matter. Another reason is that it has beautiful spin-offs. I will show you some later: proton decay, supernova, dark matter. But I think, well, the real reason is, what is the alternative? Are you going to stop doing experiments? So you have to continue, and hopefully something good will happen. But I think the real motivation would be that to find new physics. And I have 2 theory slides. This is one theory slide. I told you the case is as good as for the LHC. We actually have our hierarchy problem, just like the LHC. The ratio of the mass of the electron neutrino to the electron is something like 1,000,000. This has to be explained, independent of physics. This is a hierarchy problem. You cannot understand neutrino physics or the standard model before we understand this. The other reason, of course, I always thought it was a pity that the neutrino mass wasn't 0, but it's too late for that. That would have been a real symmetry. The other reason, of course, is that we not only have a hierarchy, we have a high mass scale. You've seen this slide many times. The idea is that neutrinos are light because they have the mass, a high mass in the denominator, and this high mass can be connected with SO10 ground unified theories or with seesaw. It doesn't really matter what the scheme is or how you want to think of it, but the charged leptons are proportional to little v of the standard model, and the neutrino mass are divided by this scale. So, discover new physics, you go and look for it. And the most direct way to look for it is this plot, is double beta decay. If you find double beta decay, you see that we are on the track of the previous slide, and you have discovered new physics, lepton number violations, and that's, of course, would be a great discovery. You see where we are. I'm a little bit out of date on this, but this is incredibly difficult. And so the question is whether we can really scale up these experiments or have to do something like Nygren and friends and go and look for a new technology that can maybe bypass this. I don't know the answer on this. But look, this is the Darwin experiment. I chose this because it's called ultimate. And you see it barely made it. Sorry. It barely makes it to where you really want to be. So this is going to be a long haul and difficult, but very interesting. So of course there's the long baseline that was triggered by the large value of theta 1,3, and which was considered a cheap way of doing it at $1.5 billion. And so this is not an easy experiment either. It's certainly, and I don't know if this is really appreciated, but liquid argon has provided these beautiful detectors. But now you have to build 40 kilotons of it and bring it down a mine shaft in South Dakota. And this is just a prototype of the detector now being built at CERN. This is going to be an incredible enterprise, and so I'm looking forward for it to succeed. And just in case you don't know what scaling up means from 1.1 kiloton to 20 kiloton, that's what it looks like. So another ambitious, beautiful future experiment is, of course, Hyper-K. But, you know, I'm worried. This was Hyper-K when I made this slide the first time, and it's shrinking. Just like Dune was shrinking until P5 came in and, you know, told them you cannot do this. You have to do 40 kiloton and, you know, 1,000 megawatt or 750 megawatt. So I really hope that there is a second module to this or a detector in Korea. We shouldn't lose ambition. Let me quickly go over this. Talking about new physics, this is again this plot, it's zenith angle, is a plot of zenith angle versus energy. Here you see the neutrino oscillations we love. This is where you look, they have this resonance for sterile neutrinos, but there is new physics like Lorentz invariance violation or violation of the equivalence principle. It's happening, you get oscillations here, not here. And that is a big opportunity which is being explored. What it actually does is, the concept is very simple. If we don't know how to violate Lorentz invariance. What you do is you kind of introduce there must be a preferred direction. And if there is a preferred direction, what you do is you do like nu mu to nu tau oscillations in different directions through the Earth. And the preferred direction of the Lorentz field will tell you that your measurement changes. You find different oscillation properties. And so you can do oscillations this way and see if they are the same, and they are. And this has been, this is a complicated business, but it leads to measurements of the changes in the speed of light that are on the order of 10 to the minus 27. And so it's competitive with any other measurements ever made. So new physics can come out of these experiments. The universe, I think there is no doubt that the universe can tell us something about neutrinos. This is where we live. And where we live is different depending on the mass is 0 and the mass is 4 eV, as you can see. And I think if we find new physics in this, it will be cosmology, not neutrino physics, but I hope I'm wrong. This is pretty much the similar picture. And so the status now is that sigma mu is less than 0.12 eV. And this actually is very interesting. This really begins at the 3 sigma level to rule out light sterile neutrinos. And so, however, you know, this is based on assuming the cosmological constant and dark energy. And so if something goes wrong, then this goes out of the window. So now, my bias is that the biggest thing that will happen in neutrino physics in the next years is a supernova. And you all know about the past one. There it is. That was a star. There is the supernova. 24 neutrinos, we may argue about the numbers, and thousands of papers, almost all of them very interesting. It's incredible what we learned in astrophysics and particle physics from 10 seconds of data. So the workhorse in this will, of course, be Kamiokande and eventually Hyper Kamiokande. You see here the single tank and the two tank numbers. You know, like, we're talking about 50,000 events, not 24. And by the way, you don't need hyper-K. Kamiokande has thousands of events from 10 kiloparsec, which is the average expected distance. And just a side remark. Past supernova is within reach of Kamiokande in these experiments too. It's sitting here, hard to reach between solar and atmospheric, but it would be great to do this measurement, and I think Kamiokande with gadolinium will succeed in doing this. We'll have detectors that can detect electroneutrinos, just antineutrinos, and electroneutrinos give you this bump at the start of the supernova, which is incredibly interesting. And you see you can measure with Dune. This may not be competitive with Super K, but with Dune you can measure this, this peak rather precisely. IceCube is in this game too. IceCube is simple. Here is one of our photomultipliers, just one, and this is the ice. And what happens when a supernova happens, for 10 seconds, all these 20 MeV positrons, antineutrinos, produce positrons, which produce a little electromagnetic shower that's long. And it radiates Cherenkov photons. And so the result is that your detector looks like this for 10 seconds, 3 seconds, whatever. And in fact, you can make a very detailed movie. From 10 kiloparsec, you get 1 million events. You can actually measure the neutronization peak, the peak I showed in the Dune experiment. And from measuring the multiplicity of photons in the photomultiplier, you can estimate the energy of the neutrinos. So you can make a movie with 1 million events. This is 10 kiloparsec. And make a detailed movie, and you can know where every photon is to 2 nanoseconds. So, you know, the opportunities, there are of course many other experiments who will make their own measurements. I actually don't know which detector this is, although it's most likely IceCube, but that's besides the point. What this slide shows you is what a peak look like when in a vanilla supernova using 2 different simulations. And this shows what happens if you produce a quark star or a black hole. But what I want to show you is that, of course, you can, you know, maybe tell normal from inverted hierarchy. But when a real supernova happens, you cannot choose between simulations. You will have to figure out what a progenitor is. And so this will, with this precision data, be an enormous process for which we will learn very much of disentangling the particle physics from the astrophysics of the event. So now let me say something about cosmic neutrinos. So they were not discussed except Christian, who ran out of time. So let me say a little bit, 10 slides. I'm using my prerogative as a speaker. They were built to, this is the universe in different wavelengths of light, and you realize the universe stops in light at around 100 TeV, but it doesn't stop in astrophysics or astronomy, we know there are cosmic rays at much higher energy. And so there is about 20% of this universe that we have never seen. And so the old idea was to map this with neutrinos. By the way, the reason the universe is opaque at high energy is that it's filled with microwave photons, and 100 TeV gamma ray will never make it to the Earth. It will pair produce, make two charged particles, and then it's charged particles you cannot do astronomy with because of magnetic fields. So Ice Cube is a totally straightforward Cherenkov detector, 1 cubic kilometer of ice with 5,160 photomultipliers. Important is that this experiment will be joined soon. I already mentioned Orca, but in off the coast of Italy, a collaboration is measuring a very ambitious upscale version of Ice Cube with new techniques that are more efficient at deploying strings and based on the experience with Antares. And it's a detector. Ice Cube has 86 strings, if that's how you want to compare it. This will be eventually a detector with 220 strings. So this subject has a future. Of course, the fascination with cosmic neutrinos is how do you really, does nature produce, 10 to the 20 electron volt protons? And the real goal is to figure that out. And, if you want to think, if you built the LHC to produce the highest energy cosmic rays, you would have filled the orbit of Mercury with LHC magnets. That's presumably not how it happens, but we don't know how it happens. So we build Ice Cube with the goal of solving that problem. Of course, neutrinos only come from sources where pions are produced by cosmic rays. So you see the sky in cosmic ray sources. This is 1 year of Ice Cube data, and this is in galactic coordinates. We don't see the galaxy, which you expect to see first. In fact, the first source we see is not even a nearby extragalactic source, it's 4 billion light years away. So who can explain that? So there are 140,000 candidates in this map. By the way, the structure you see is the absorption of the Earth, of the higher energy neutrinos. So you're looking at the shape of the Earth. And of course, that we can use to measure the cross-section at these energies, which we have done. In this map, there are 120 cosmic neutrinos, and we found them. And 12 are clearly separated from the atmospheric neutrinos that dominate this map because they have too high energy to be produced in the atmosphere. And those are the ones you know and always see in the talks, right? They have energies above 60 TeV. So how do we do this separation? Well, just like Super K, we look for events starting in the detector. This is a 1000 TeV electron neutrino. Or we look for muons coming through the Earth that must have been produced by a neutrino somewhere under your detector. This is a 7000 TeV neutrino. And so that are the two methods. These two methods give data that perfectly agree. Now to come back, this map was totally uniform. We spent 5 years looking at this map, trying to find anything but total sphericity in it, totally unsuccessful. So not knowing anything else to do, we started doing this. What we did is whenever there was an interesting high energy neutrino produced, we had the computers at the South Pole reconstruct the coordinates where it came from, and automatically this one, within 43 seconds, send the coordinates to every telescope who wanted to look in that direction and see what happens. We actually had no idea whether anyone looked or not. And so this was the neutrino 9 September 22 of last year. And so It turns out that in the direction of that neutrino, there was an active galaxy that had increased its intensity over the last few weeks by a factor 7. And right at the peak of this neutrino came. In fact, the galaxy picks up daily variations, goes crazy, and then the neutrino happened at that time. In fact, the coincidence was 0.06 degree. So the amazing thing is that we were pointing in the right direction because our resolution is not that good. And we know we're pointing from the shadow of the moon, but that's for one TV muons, not for a 380 TV muon, which this was. So, surprise, magic looked, and this object is one of the rare objects that emits TV gamma rays. In fact, it turns out this object, just like we don't see the galaxy, it's not nearby. They measured the redshift, and it was at 4 billion light years. So it must be something special about this source. This is a long story, but I think this only becomes the accidental. This could be accidental. The chance of this being accidental by every a posteriori estimate is smaller than 1 in 1,000, but it's only 1 in 1,000. It's 3 sigma. But then you can do something. Now you have a specific direction in this map. So now you can start over. And you have a priori opportunity to go and look at that place in your map without any look elsewhere effect. And so then there are no trials, there's no analysis, the prescription is old in IceCube. What it is what it is. So we look back in our data, and this is the last 9.5 years of data. Now, I guess most of you are looking at the wrong spot. This is what I've been talking about. This is what we found. In 2014, this source burst, and it emitted 19 neutrinos on a background of less than 6 in 150 days. You know, if you look for galactic sources, you look for 2 or 3 high-energy neutrinos in 5 years. This was 19 in 150 days. So there is no doubt, there are no trials, no, this is real. The chances of this not being real is like 1 in 10,000. I don't care about whether the previous observation was accidental or not. So what is this source? It's a blazar, it's an active galaxy. So it's a galaxy like ours, probably 1,000 times heavier, but it's actively accreting matter at high rate. And then it builds up an accretion disk and magnetic field, and the magnetic field eventually can launch a jet along the rotation axis of the supermassive black hole. And so a blazar is a special case where this jet is actually pointing directly at the Earth. And so neutrinos come in because obviously there must be protons accelerated somewhere in shocks in this jet. And then it interacts, for instance, these galaxies glow in blue light. And they can pick up a blue photon and produce pions and make neutrinos. So this was kind of anticipated. In fact, you have to know good old physics. You have to know what a delta resonance is to understand the blazar. And so, as I said, this one was pointing at the Earth. Our most important discovery is, though, that this shows the flux of neutrinos. These are our early measurements. But you know, everybody in this audience knows isospin, unlike when I'm talking to an astronomy audience. You know that for every pi plus and pi minus that made a neutrino in this picture, there was a pi 0 that makes a gamma ray. Nobody has seen 1,000 TeV gamma rays, and the reason is that is this. these gamma rays don't get here. But these electrons will radiate and then pair produce again. So eventually the energy in this gamma ray ends up as many low energy photons. And so if you work that out, any theorist worth his salary can do this, you say there is an equal flux of gamma rays, it doesn't matter whether you cut it off or not, and you calculate the number of photons, you get this. And this is what Fermi satellite sees. So I won't sell this to a factor of 2 or so, but what you learn from this is that the energy in the high energy universe is that neutrinos are as common as photons. They carry the same energy density. And we never will understand high energy astrophysics without neutrino experiments and proton beams. So back to particle physics and back to neutrino physics. Where is the new physics in this? Here it is, and it's just boom. You've already seen an electron neutrino, you've already seen a track. How do you see a tau neutrino? You see a tau neutrino because the things that in donut travel a few millimeters travel 10 meter, 50 meter in ice. So 50 meter per 1,000 TeV. So you can go and look for the production of the tau and then for its decay. And you can see them separately. And so this was the first measurement. This is, of course, important because neutrinos detected over this large distance oscillate and have to be arrive with equal flavors at your detector. And so this was the first check we make. And you see this is the number of nu tau, number of nu mu, number of nu e. And so you have to end up here. And so that was the first measurement. And the reason you find this line here is that you cannot tell nu e from nu tau. And you end up at all nu e. But this is 1 sigma, you see. And so we did this measurement. This was 4 years of data with 7 years of data. And we noticed that we actually found a point between nu e and nu tau. This is done with statistical analysis. So we went back and looked in the data. Why the hell does this thing sit there? It must have found some evidence for nu tau. And in fact, it found 2 events. And one event is the event Christian showed. And so it's a nu tau that traveled for 17 meters through the detector. And you see, he pointed at this. You see, these are the photons detected by one single module. And you see the profile with the tau production. What he didn't say is, this module was actually not part of the fit. It's a prediction of the nu tau fit to the event. And I could fish out many like this. This was serendipitous. An analysis is about to be unblinded. That should do better than this. So we'll come out with nu taus soon. Where is the new physics? Well, it's oscillation, but the new physics is easy. You know, your beam starts somewhere. If your beam is neutrons, it's all nu e. You are going to oscillate and end up near here. If it's all nu mu, you end up here. And wherever you start, you assume pion and muon decay, you end up here. You have to end up along this line. And so if we end up doing a precision measurement, and we end up anywhere outside this line, we have discovered new neutrino physics. It's that easy. And so our first phase, the experiment I mentioned, where we are going to launch our R&D for the next generation detector, will, in a few years, will reach that precision. So this is probably the most exciting thing I can think of for the future. Christian mentioned production of a W. Of course, neutrinos interact with the nuclei. They don't see the atoms. except an anti-electron neutrino can produce a real W on an atomic electron. Glasgow pointed this out in 1959, actually. It was published in 1960, but he was a postdoc of Niels Bohr at Copenhagen, and he gets everything right, and then he says that if you build a 1 kilometer cube underground detector, you will see 2 events per day. So we see 1 event in 8 years in a kilometer cube detector. What he got wrong, of course, in those days, you didn't know the mass of the W. So it could be light, and for every atmospheric muon, you could have an atmospheric nu mu that produces a W this way, or a nu, and its accompanying nu E. So I don't think his calculation was wrong, but it also puzzles me because, if you take Fermi 1936 paper, from dimensional analysis, you can translate G to a mass, and it's 40 Jeff. So within a factor 2, they could have known that it was not going to be 2 GeV. Anyway, this is our event, and it's not contained in the detector, it's just outside, where it was found in a different analysis. And it's exactly, if you correct for the Cherenkov light that the photomultipliers miss, you end up at exactly 6.3 GeV, and you end up on this resonance. So this is the event, W goes to QQ bar. And so this is the first time we see a cascade that we suspect is not electromagnetic. It's a QQ bar decay. And so it must have muons in it. And so you can actually go and look at the muons, because if the thing is produced here, it will produce a cascade which radiates the usual way, but the muons go at the speed of light and race ahead of the cascade. The cascade goes at the speed of light divided by the index of refraction, 3/4. And so you look at the right string, you will see the muons arrive ahead of the cascade. And in fact, at this point, I cannot show you the data, the paper is being written, but you can reconstruct both the cascade and the muons. And so we actually have a test of reconstruction in this business. So I am way over time, I'm sorry. I was going to tell you about, but the question was answered by Christian, about radio detection, which you should not forget. And in fact, there is one beautiful idea that's new. Radio detectors detect neutrinos with antennas just like we detect them with photons. The new idea in this game, which is very old actually, but is picked up again, is to put detectors on a mountain and look along the horizon for taus that are interacting in the earth and then decay in the air and make a shower. And if you sit on a mountain, you can look everywhere along the horizon and build up a large solid angle. And you can do this with radio, but you can also do it with Cherenkov detectors. And I think this is an idea that may have a brilliant future. And it's still relatively cheap, it's not long term. I'm looking forward to this. You may, of course, go and look at, not at the horizon, but look down at the whole Earth. And that's also an old idea, which is being revived in this detector. These are my last slides. One thing I have to mention before, in order not to miss a prediction, is gravitational waves. When neutron stars collide, and that event, of course, these are the dates of multi-messenger astronomy. August 17 I haven't discussed yet, and August 17 is when LIGO Virgo saw the merger of 2 neutron stars. This is a simulation, and you can imagine you build up an accretion disk that then launches a jet, just like an active galaxy. It's very similar physics. And you should see neutrinos. And we didn't. In fact, Auger was in the right field of view. We didn't see neutrinos. In fact, if it had been in the other hemisphere, IceCube had the sensitivity to see it. Now, do you know the sensitivity? You know, maybe. But when I say IceCube should have seen it, all the physics is already, is the physics that we know and love. And there is the jet, and this is the accretion disk, which now is a spherical ejecta called the kilonova. And if you do the calculations, I'm not going to go through this table, but you can now put an error bar on the calculations. And if there is an event like this that happens in the next run, of course, the idea is we didn't see it because we weren't looking in the direction of the jet. But eventually, we should see this object, and hopefully that's happening in the next few years. This will be a great opportunity for neutrino physics to contribute again. So I'm sorry, I'm finished. My conclusion is the first line. Neutrinos were never boring, and they will never be boring. I mean, given the instrumentation we are developing, this is going to be a field that's more exciting than it is now. We should not be shy about going and ask for money and compete with anyone else who asks for money, because we made great discoveries. We may discover a supernova. We discovered physics beyond the standard model, geoneutrinos, soon past supernova neutrinos, cosmic neutrinos. We have all the arguments to go and ask for bigger and better detectors. Some neutrino physics is still possible at relatively low cost and short time scale, which makes it also attractive for those who are not as young anymore. And if not, so be it, and do it anyway. I mean, there's no reason these experiments should be an order of magnitude cheaper than many other things that have been done. So that's it. Go and do it.
Thank you very much, Francis, for this nice overview. I don't think we will reopen the debate and discussions, and I think we should really warmly thank Francis again for having shown that the future is very bright in neutrino physics for the coming years.